Okay? This is one of the big major restructurings that I did within the Chem 130 class for this class in particular, okay, for the English learning community. And I liked it so much that it is now how I teach Chem 130, is this full restructuring. So we go pretty much right into atomic theory. How do we build an atom? Okay, what makes up an atom? I was pointed out by an observation made by a colleague that what I end up spending probably the next 45 minutes talking about is talked about in like a paragraph in your textbook. Okay? Because the textbook doesn't find it important, I do. Okay? What we're looking at is effectively the history of the discovery of an atom. Where is it coming from? How do we learn from it? What are we evolving from? The biggest, or one of the original discoveries, is going to go all the way back to Dalton, okay, in the early 1800s. So he went through, based off the information he had access to, and tried to come up with some parallels to explain the observations that we found in nature. Okay? So we've got a periodic table that we haven't discussed yet on the walls. And if we take a look at the image on the slide, that image on the slide looks drastically different from the big posters on our walls, and yet what are they representing? It's the periodic table of the elements. It's the same thing. There's a couple massive differences. What are those big massive differences?
Using symbols instead of letters.
Okay. When Dalton put his together, he's using symbols. Okay. So instead of saying C or N or O, he goes circle with a dot in it, circle with a snowflake in it, circle with a triangle in it. Okay, why? It's kind of a personal preference behind it, but when we think back to kind of the origins of science, a lot of it was rooted in mysticism, okay, or magic. So we come up with weird symbols, and everybody goes, oh, weird symbols, that must be really cool, they must be really, really smart. And now we're starting to realize we need to stop convincing people or scaring people away saying it's magic. It's not magic, it's just a bunch of letters that we mash together. Okay? And that's where we've kind of transitioned to. Other things that stand out as different to you. The number of elements. Okay? Our element was the smallest indivisible piece, at least according to Dalton. That is Dalton's periodic table, right there at the top. 2.5 rows, okay? Not even close to the 118 we currently have. Why is he only looking at that few elements? It's exactly
That's all he had the ability to discover at the time?
That's all that has been discovered. Okay? The other elements were out there, we just hadn't come up with ways to purify, to identify them. So that's really all he had access to. What's underneath it? The bulk of that image is now a bunch of other stuff. Those are compounds. Okay? So he went through and said, well, I can combine, say, circle with a dot and circle with no dot, and that makes a compound. Okay? I can call that compound by a name, or I can now show it in this pictogram type method. Yeah?
I think you have a typo on the last one. Is it to form different compounds?
Yeah, we'll get to that. Okay? What happens as we continue through the rest of the images? So we add more and more atoms. Our pictures get bigger and bigger and bigger, right? Okay. We think about, I don't know, a human being. How many atoms are there? Lots and lots and lots and lots and lots of atoms. Do we really want to build or look at our representation for the formula of a human being with a bunch of circles?
Take up the whole room.
Okay. That's going to take a lot of drawing. So we had to change our notational system to represent that. And that's largely why we end up with the symbols we've got. Okay? So let's kind of move through Dalton's atomic theory. And because you've read the textbook in theory, you should also be able to tell me which of these is wrong and why. Okay? An element is composed of tiny, indivisible, indestructible particles called atoms. Can't we split an atom? What do you mean?
A lot of bad stuff happens when you do.
No, not necessarily.
Nuclear explosion.
Not necessarily.
Built in even smaller things like electrons and protons.
We have electrons, protons, and neutrons. Okay, so there are constituent pieces to atoms. So if we look at Dalton's theory, he had the right idea, and at least in the 1800s, that's all they had to work with. They couldn't get smaller than those atoms. Okay? But it turns out this indivisible and indestructible particles, not true. Okay? So that first theory is wrong.
Wait, wasn't that Aristotle in the textbook said that was Aristotle's belief? and it was
Aristotle
like 21
contributed to
centuries,
it,
and then Dalton
yeah.
was the one that.
Dalton formalized it and collected it all as his own rules.
Do you still want us to make like this whole thing about like that's
Yes.
like, obviously a
These are all
part of-
part of Dalton's atomic theory,
Yeah.
okay, or credited for him. It is built on the backs of other scientific achievements. Okay? Some of those scientific achievements didn't have evidence, it was just someone's theorizing. Dalton gets credit for most of these, primarily because he could come up with experimental evidence to support it. Okay? All atoms of an element are identical and have the same properties. Okay, that is also wrong. Why is that wrong?
They don't have the same properties.
Okay. So there's a possibility. What was that?
They don't have the same properties.
Ions don't have the same properties. Well, ions
Different charges.
aren't listed on here yet. We end up with this concept of charges. So a different element, or the same element, can have a different balance of electrons in comparison to its protons, which changes its charge, which changes its properties. Okay? We could also change something else without changing the element. What happens if I change protons? Start with hydrogen with how many protons? Just kind of testing you based on what you picked up from the reading. Hydrogen has how many
Hydrogen has
protons?
2 and
Hydrogen has 1. If I add another proton, do I still have hydrogen? No. What do I have?
helium.
I have helium. So I can't change the number of protons. I could theoretically change the number of electrons and still have hydrogen. What else could I change?
So what exactly does that mean when you like hydrogen with one electron and hydrogen with 2?
That would change how it interacts and sees the rest of the world. And that gets into charge, which we aren't quite to yet. Okay, so we'll hold off on that analysis. We could also change the number of neutrons. Okay. The electrons are going to change the charge. And I'm having a lot of trouble with my pen as of lately. And the neutrons change the...
It makes it unstable.
Not necessarily. Just changes the mass. We will reach limits where if we change the number of neutrons or the number of protons, we can change stability. Okay? But that's a further down conclusion. Initially, our neutrons will change the mass without changing the identity. So the biggest issue there is probably all. Okay? Not all atoms of an element are identical.
How do you add or take away neutrons? It's not like they just have a jar of neutrons sitting around.
The
It's like we're going to add 3.
physical process of doing that, or the chemical process of doing that, we don't have easy access to. Okay? So what we would just do is say, theoretically, what happens. It's happened somewhere. What does that mean? Okay? Atoms of different elements combine to form compounds.
True.
If I take hydrogen and I combine it with oxygen, I have the potential of making water. Okay? Water with the formula H2O. So I can take different elements and combine them, and we end up getting new, wildly different things, okay, with different properties. Hydrogen's a gas. Oxygen's a gas. We know both of those to be gases because this reviews back to Thursday's lecture, which I thought we covered. There we go. We've got this lovely periodic table on the wall, and both hydrogen and oxygen are red, and according to the key at the bottom, red elements are gases. When I take hydrogen and oxygen and I combine them to make water, water is a liquid. Okay? So I can change some of the properties of what we're visualizing by changing the amount of elements that go into it. Okay? So 3 is still true. 4, compounds contain atoms in small whole number ratios. When I make water, it's H2O, meaning I have 2 hydrogens and 1 oxygen. Okay? So we're looking at whole number ratios. I can't take a fraction of a hydrogen and a fraction of an oxygen. They have to be whole atoms. this kind of goes back to, admittedly, a false statement. An element is composed of tiny indivisible particles. Okay? Compounds are composed of smaller particles known as atoms. Those atoms need to come in whole units into our compound. Okay? Just because I can further break down an atom doesn't invalidate the other steps. Make sense? Last one, atoms can combine in more than one ratio to form different compounds. True. Okay? With the horrible, horrible joke, two men walk into a bar. The first one says, I'll have a glass of H2O. The other one says, I'll have a glass of H2O2. The second one dies. Boo. Because H2O2 is also known as hydrogen peroxide, not water. That's going to kill you. Okay. No. No. Well, concentration makes the poison, so that's a question for a different lecture. Right? So the first two rules in Dalton's laws are wrong. Okay, we have since learned enough to invalidate those. The rest of them are still true. Okay? So, where do they start becoming false? We go all the way to the late 1800s. So we're roughly 100 years later, ballpark. We get Thompson. Okay? For those of you doing fan letters, oh, that's right, you all are. We just talked about Dalton, and we're now about to talk about Thompson. That could be relevant. Thompson discovers two subatomic particles, electrons and protons. Electrons were the primary discovery, and then protons by corollary. Okay? By corollary meaning if I have electrons, I know I have to have protons. Okay? The electrons he discovered to be negatively charged. Okay? Are negatively charged things reactive? I don't know, Mike. That's an interesting question. Okay? Well, one quick way to figure this out is find a source of electrons and touch them, see what happens. For reference, don't do that, but we could take a fork and shove it in the electrical outlet. What's in the electrical outlet? Electricity made of electrons. What happens when we stick that fork in the electrical outlet?
They go through our body.
They go through our body to try and find a neutral source, okay, to cancel that charge. Okay, so almost everything we're dealing with is an attempt to cancel charge. If he's now discovered electrons, and we can look at the rest of our world and say, well, when I touch the table, I don't die, the table has to be neutral. Okay, there has to be something canceling that negative charge. Thereby, if I have electrons, I must have the counterpart protons. Okay, that then cancel each other out. Okay? As far as the charge, he was able to determine that they have relative charges. So when we say an electron is -1, we aren't saying that if I take the unit for measuring charge, which is technically a coulomb, that it is 1 coulomb, okay, or 1 charge unit. We don't have that. All he knows is that it is negative, and that protons thereby must be the opposite, which will be positive. How do we assign negative and positives? Well, that comes back to his experiment. The experiment hinges on a very interesting discovery, and this is why we did not actually discover electrons until the late 1800s, was because this discovery was not yet made. What discovery might that be?
Neutrons?
Nope, neutrons are way later. They're about 20 years later, 10 years later. Nope, we don't even have a nucleus yet.
Oh, what, like the technology to look at it?
Like a microscope, we still can't see electrons. We can see the evidence of them, but we can't see electrons.
Oh, yeah, well, oh, wait, back then you're talking about.
Electrons are high energy things, right? Okay. So how often am I going to be able to go out and just say, whoop, there's an electron? Never. As soon as I reach out, I'm going to end up canceling it. Okay. That's something that we have to consider. So if let's say I've got electrons and I try and make an electron beam in air, what's going to happen when the electrons come out?
You're going to get charged positively?
They're going to hit matter. What matter are they going to hit?
Electrons.
Air. They're going to hit anything that's out there. What happens the instant the electron hits that air? Becomes neutralized. We cancel the effect or the evidence of that electron. So how can I possibly discover an electron then? If every time it comes out, it hits something.
Because they avoid each other.
I have to remove all things to allow for the electron to exist. What is the thing that has nothing? A vacuum. The discovery hinged on the creation of a vacuum. If we don't have a vacuum, we can't do this. That was the best picture I can come up with for a vacuum. And I thought it looked pretty good. Okay? With that vacuum, what they could go through and do is take a small glass container, evacuate all the air using a vacuum, and then what they could also do is apply an electric field. They put a little metal rod at one end, a little metal rod at the other, and they put a ton of electricity in behind it. Okay, well, electricity will flow through metals, so it doesn't flow through air very well. Okay, but if you build up enough current, the electrons will try to neutralize. The only way it can neutralize is if it jumps through the air. In the process of jumping through the air, what do we end up noticing? We noticed this fluorescence, this colorful beam came out of it. And what we had was known as a cathode ray gun, later adapted to a cathode ray tube. We may have heard of as CRTs, which are then typically compiled in an array to make television. You ever gone back into your probably grandma's attic and find that giant, massive box? There was a TV. Those were CRTs. Okay, we've since updated our technology where we don't need thousands or millions of tiny little vacuum tubes, and we can instead use LEDs. Okay? But that's what these are. Effectively, a single pixel of a TV, of an old school TV. We could then study that by putting magnets up near it. We would notice that the beam bent. Why would the beam bend? Well, the magnet has a pole associated with it, a positive and a negative pole. If you align it one way and you see the beam bend, right, you now know something about what that beam was made up of. Kind of neat, at least in my book. Questions? Yeah?
Is that like that ball with all the electricity when you put it at one point on your finger on it?
I don't remember what those are, but no. Those aren't the same thing. They have a similar principle, I think, behind it, but they aren't cathode ray tubes. Okay. The other big thing coming out of cathode ray tubes that we'll talk about here in a little bit is one of the initial discoveries, or one of the reasons why we started poking around at this, was the discovery of elements like uranium, or plutonium, or radium. What do you guys know about any of those elements?
Radioactive.
They're radioactive. We took an object, we put it down, and all of a sudden it's starting to do weird stuff around us. Okay, why is it doing that weird stuff? Okay, we took a chamber that has nothing in it, I apply current to it, and all of a sudden stuff is happening. Okay, we're seeing invisible things happening that have no explanations. We come up with the explanations. Okay, so Thomas is famous for his discovery of the electron. Once he had the electron, he then went through and refined that and applied that to atomics, or atomic theory. So he came up with a model of the plum pudding, 1903. Okay? Time's not super important here. Said atoms are a sea of positive charge, and they have these plums that are electrons floating in it. Okay? And that's his model. That means there really isn't any mass. The mass is just kind of this overall positive charge, and we just have electrons chilling in it somewhere. Okay? So he is famous for that. He's also famous for that because it's wrong. Okay? But based off the data he had, that was a reasonable conclusion. We know we needed negative, we know we needed positive. So we just put them together and just said, let's see what happens. Okay? Before we get into Rutherford, this one's not in your textbook. Millikan and Fletcher, in the combination of eyesight and patience, were able to determine the exact charge on the electron. So if you scroll down or look at the bottom, we've got this little number down here. That number, as far as I'm concerned, is meaningless with this class. I'm just putting it there because 10 to the minus 19, is that a big number or really small?
Really small.
That's a really, really, really small number. And so it's kind of amazing that they were able to make a measurement to measure that charge. So they came up with the exact charge. The other reason why I like this is the experiment itself. Okay, so we got a rough picture there. Seen those little perfume or cologne things where you squeeze a bulb and it spits stuff out? Usually perfume. Okay. Turkey baster could kind of work too, but a little bit more refined with our turkey baster here, and we filled it with oil. The interesting property of oil is oil will carry a charge. So we spray those little oil droplets into a box. Okay. At the bottom of that box, we poke a tiny, tiny little hole. A hole just big enough that an oil drop could fall through it. So I spray my little oil thing, and then I look on the other end of the hole, and I hope to see an oil drop fall through. I don't want to see all of the oil drops. I just want to be able to catch one at a time. And since I can't create a mister that only gives me a single drop of oil, I just have to eliminate all the others. And that's why I have that tiny hole. On the other end of that hole, I now have a microscope set up so that I can see an oil droplet fall through it. Okay. Well, cool, you built a really fancy way to see something that is now tiny and watch it fall. Okay. I could take an apple and watch it fall too. That doesn't do anything. What they added to this is a sequence of charged plates at the bottom. So Thompson said our electrons were charged. The oil droplets will carry that charge. So they're negative. Well, those charged plates are set up with a very large negative and a very large positive. What happens when that negative electron falls through that hole and starts to move towards that negative bottom plate?
It'll curve downwards.
No, it would be pushed away, wouldn't it?
It's going to be pushed away.
It's going to go
Oh,
up.
yeah, because it's the same.
The negative charges are going to repel.
Yeah.
So what they can do is look through the microscope, wait till they see an oil droplet, and spin a little knob. That little knob will now adjust the voltage across that gap. Okay? And they will adjust the voltage to hopefully not let it hit the bottom or the top. They'll adjust it till exactly what point?
Till it's evenly balanced. in the
Till
middle.
it's evenly balanced and the drop is no longer moving. It is stuck perfectly level. Okay? Why is it perfectly level and not moving? There's the downward force of gravity causing it to move down, and the upward force that is now equal and opposite of our electric plates. Because I know the electric current that I'm dialing in, I know now how much charge is required to keep that up. Because I know through the microscope the size of the oil droplet and its density, I can determine its mass, and I now know the downward force due to gravity. I can set those two equal to each other, and I can determine the charge on an electron in an oil droplet. Freaking nuts. Okay? Add to that, I remember tiny oil droplet, microscope, charge, lots of little variables that are initiating in here. What are the odds they did it right on the first time? Very, very slim. So that guy had to sit there and play with this a whole bunch. Eventually he gets it right on the first time. Okay? What are the odds he made a mistake in the measurement? Probably pretty good. So we need to do it a second time so we can average out that mistake. You probably screwed up the second time too. And the third and the fourth. So they probably repeated this hundreds, if not thousands of times, averaged all of those results to end up with the charge on an electron. Again, microscope, little knob, oil droplet, perfect timing, floating, now I can run tons of calculations. Really, really neat. The extra thing I like to add into this is which of those two people did probably the bulk of this experiment.
I feel like they have to switch back and forth.
Fletcher. But if we look up who discovered the charge on an electron, 9 times out of 10, what you will see is Millikan. Well, if Fletcher did the work, what did Millikan do? Millikan was the teacher. Fletcher was the student. Remember, you guys writing fan letters, right? Okay. So a rough equivalent, you turn in a fan letter to us, we go, holy crap, this is a really good fan letter. I like this. I'm going to publish it. Okay. In this class, guess what we would do? We put your name on it. We'd say we were the teacher and publish it. Guess what happens in science? I'm going to erase your name, and I'm going to put my name on it, and now I publish it. Okay? Depending on, and that's just how science has been generated. The principal investigator gets the credit. Depending on the principal investigator, on if they're a reasonable person or not, they will also allow credit to go to their workers. Okay?
Even if the worker was the one that came up
with the breakdown?
Yep, all the way through.
You could,
And there's nothing you can do about it. Okay? I can't speak to Edison. I don't know that one. Okay? That is how science is designed. Okay? So what does Fletcher then do? Well, Fletcher is actually a pretty good guy about this too. He's since talked about it and been like, I don't care. That's how science works. The principal investigator gets the credit. Millikan contributed a lot of intellectual property into the design of the experiment and how to do it. Fletcher was the hands. Okay? So Millikan does deserve credit for this. It's not like, oh, well, Millikan's a jerk for stealing everything. He didn't steal everything because we still talk about Fletcher. Okay? But the intent is just to see how science sometimes works.
When we get to the scientific aspect of writing, we'll talk about like academic publishing and like what types of sources you use for publishing.
Sounds kind of shady.
Okay. It is. But it's also kind of fun. After that, we move into Rutherford. And we get Rutherford's model of the atom. Okay? So Rutherford, see, this is an interesting parallel. Okay, right? On this last one, we said Millikan and Fletcher. On this next one, whose name do we see? Rutherford. And the very first sentence says, Rutherford's student. What was his name? Well, I don't know. Okay. Rutherford was also a really brilliant, kind of bizarre, crazy guy. He was probably heavily involved in this experiment. Okay? So what they went through and did is they fired alpha particles at thin sheets of gold foil. So the gold foil is thin enough that we can see through it. What is an alpha particle?
How do you necessarily send lead alpha particles lead through something?
Well, that's what we'll talk about because that's part of this. What are alpha particles first? Yeah, alpha particles are positively charged atoms. Okay? In particular, they're positively charged helium nuclei. They are radiation. They are nuclear radiation. Okay? So if I want to go out and say, buy some alpha particles, I have to find a species that releases that radiation. Okay? So I can just go to the local store and I can buy uranium. No. Okay? Well, let's say I somehow get a hold of some uranium anyway. Okay? Now I have hold of uranium. Does that mean I can make a nuclear bomb? No. What do I have to do? There's a theory behind the purification of uranium to make a bomb, so that it's pure enough that we can actually get that facility or that technology. That's why countries like North Korea and other countries, Iran and everybody else, we aren't as concerned about them just getting a hold of uranium because you have to be able to purify it. We have access to uranium in lots of different places, but we have to have that purification scheme, and that requires lots of strict mechanisms. Why do we care about purifying it? Well, if it's not purified, then it's not predictable. Okay? Do we really want something that is not predictable, either in the military or in science? No. Why not?
it's too crazy of a variable.
In a military situation, if it's not predictable, it could blow you up. That defeats the purpose of building the bomb, to not kill you. Okay? And the purpose of science, the whole point, is that we can use that to predict something else. Well, if it's unpredictable here, that means it's unpredictable over here. I can't draw conclusions based on any of that data. It has to be pure. Which takes us back to that alpha particle. Okay? As Ryland was mentioning, we've got this lead. That is really just a lead box with a tiny pinhole in it. Okay? That lead box blocks the alpha particles. The tiny pinhole will allow an alpha particle through. That is now effectively building a little director. I now have alpha particles that can only come out one direction, and I can aim that. The lead just prevents it from going anywhere else.
Like, is there something on it, like, are they shooting something through the lead? Like,
So what is that weird yellowy glowing thing in the middle there?
Yeah.
Well, that is our source of alpha particles. That source, roughly equivalent to uranium, is actually radium. Okay?
Oh, so the lead is just a casing.
The lead is just a casing to focus our beam of alpha particles. So we needed that radium. I picked uranium because everybody's heard of uranium, theoretically. Okay? But radium is our source. Has to be pure. Okay? What is the issue with nuclear radiation?
There gives you cancer.
Okay, it can kill you. It's dangerous, cancer. Okay, so we've got some problems with it. We can't just go out and grab it, and we have to come up with that purification process. And remember, we just discovered the existence of an electron. We know very little about radiation. So somebody else had to come along and say, here you go, Rutherford, here's a sample of radium. It's clean. It'll do what you want it to. Who was that someone else? That's Madame Curie. Okay? Alpha particles are a radioactive source. Curie is the one that came up with that radioactive source and the purification scheme for this. Okay? Let's add an extra layer to this. Boom! I invented the cure to cancer. Step number 1 is going to be what? Patent it. Why would I patent it?
So nobody steals your stuff.
So nobody steals it. Okay, what else can I do with that patent?
Sell it.
I can now sell it, and I can make tons of money. Okay? All sorts of side ethical reasons that can come spin out of this. What did Curie do with her discovery of radiation? Gave it away. Did not patent the purification scheme, so other people had access to it. Not only that, but she released that pure radium sample out into the world where other people could use it and study it. Okay? So there's kind of a big debate in science. Do we use patents or do we have open access to information? What happens if we just have open access to information?
All these scientists that worked hard aren't getting paid for their...
Now the scientists that worked hard don't get paid for their work, and they now leave the field because that's the only reason we were scientists, is because of the money. The only reason I teach is because I get paid really well. Okay? Yes, there are scientists that are out there solely for money and ego and glory, but that's not always the case. Curie was super important because she wasn't one of those people. They released that information, gave everybody access to it. Another reason why I like to bring Curie into this. My history isn't the greatest. When it comes to science, I'm a little bit better at it, but then we look at the social aspect and I'm just afraid to talk to people, so I don't get the social part. Okay. When did women get the right to vote in the U.S.? 1920, exactly? Oh, cool. I was going to say 1929, and I have no idea why, but I will accept 1920. When was this?
The late 1800s.
1905, 1910. Women can't vote, and yet what has Curie done at this point?
Revolutionized science.
Revolutionized science by this discovery of radiation and evaluating it and allowing that radiation source to make it out into the world. Okay? Can't even vote, and yet she's making massive contributions to science. Okay? Were her efforts recognized? Okay? There's only one person in all of history that has won the Nobel Prize twice in science fields. Curie. Didn't have the right to vote, and she's won the Nobel Prize twice. Okay? Or had won the Nobel Prize. One in chemistry and one in physics. There's only one other person to have won the Nobel Prize twice, and that was also a chemist. One in chemistry and one for peace, I think was it. Actually, I don't remember. Do you remember? Pauling. Linus Pauling. I don't remember what his other one was, but it wasn't in science. That's for sure what I remember. So Curie can't vote, won the Nobel Prize twice. Pretty phenomenal woman. We talked about the whole credit aspect. She did most of her work in France, where she called home. Every country has their own National Society for Sciences. Okay? France has one too. Okay? Won the Nobel Prize twice, massive leaps and bounds, allowing us to then make the discoveries that Rutherford has done. Not admitted to the physical or to the Science Society in France. Why? To put it not nicely, she didn't have a penis. Okay, she was a woman.
Is there an international one too?
There are international ones too.
But they are
1900 communication's a little bit different. Okay. So France didn't acknowledge it. She's later been like posthumously added in to give some kind of credit.
Do you think she did the right thing?
Absolutely. Or not patenting it? Yes, absolutely. I think science and education should be free for all, period. And I get yelled at for free. Not free. It is a societal convention to make sure everybody has access to that knowledge. period. So everybody agrees to contribute to allow everybody else to have that access.
Just from a sociocultural standpoint, what would have happened if she had held on to that knowledge?
She held on to that knowledge. Does Rutherford have his radium source?
Unless he buys it from her.
Unless he could potentially buy it from her, which then means he has to be able to afford it.
There's no way she's gonna
If
get
he
business
can't
on it.
afford it, okay, then he can't pay for it. And at best, what we do is now delay the discovery of science until somebody can build up or come up with alternate pathways.
The science is still there. Someone else is gonna like if.
So Curie could sit on it, yes. The information is there, but then do we really want to wait for that time frame to make those advancements? Right? And that's where I think patents delay us, they slow us down.
What about implications for like the world war and that kind of thing? Like implications of her research?
Those eventually snowball out, but that moves another 30 years down the road, 40 years down the road, when they bring in a bunch of other scientists looking at nuclear radiation and how you can then weaponize it. And then they later went like, holy crap, that was a really bad idea. We shouldn't have done that.
So you saw the Manhattan Project?
Community like view nuclear weapons as like a mistake.
So we're getting a little bit off topic. What you're looking at then is different fields and different
Like ethics and
thoughts.
stuff like that.
So you bring in all sorts of ethical questions, and science has massive implications within ethics. Okay? Did we talk about TNT in this class?
Yeah.
TNT was devised so people stopped dying in mines. Okay, when we were trying to mine minerals out. What did we end up using TNT for?
Kill each other.
To kill each other. The intent was to not kill each other. So it can always be misappropriated and shifted into other sections. When we're looking at energy, all military throughout all of life is all about energy. Okay? You can look at food, okay? You can look at water, you can look at gunpowder. It's all about the control of energy in one form or another. Right? He who controls it, or it that controls the energy, controls everything. Okay? So, back to this.
Which is why infinity stones are so important.
Yes, infinity stone is important for that. So, plum pudding model, Rutherford, Thompson's model. Says we got electrons. What happens when we fire alpha particles at it?
They go through it.
It's going to pass straight through. Okay? I used to say Rutherford didn't like Thompson. Okay? All because of the experimental design. They were like best friends. Okay? Why would I say that he didn't like Thompson?
Because he disproved him.
They ended up disproving him. And there's a very simple adjustment that we can make to Rutherford's experiment to prove Thompson's model, or to at least supply evidence that Thompson's model is valid. All right, so let's take a look at it. We've got our radiation source. We have this blue sheet on the outside that goes all the way around our gold foil in the middle. That blue sheet is the detector of radiation. So our radiation comes in at the gold foil. If Rutherford wanted to prove Thompson right, or provide evidence to it, what did he have to do? You want a hint? It's a quiet hint.
Everything should go through one place. Like it shouldn't be like dispersed. If it's the plum pudding, it should always like have like the same pattern of shot.
If it's the plum pudding, exactly what Ian's suggesting, it should pass straight through. So where should I put the detector?
Directly on the other side.
Directly on the other side. And if we did so, what would we find? Oh my gosh, it passed straight through. It must be the valid mechanism. But what did Rutherford do instead? Put it all the way around. Okay? Why would he put it all the way around?
For science. Just
Good science. Limit all the variables. Hey, Thompson, we're just going to put it around just to extra prove that you were right. We fired alpha particles at it. Oop,
Turns out you're wrong.
something has bounced. Why did it bounce? It had to have hit something that was massive, because we're firing an alpha particle that has some weight behind it, and it has to be positively charged. So what did Rutherford then say? Well, Thompson, your model's wrong. We're going to say that there is a nucleus. that nucleus is going to have all of the protons located in it. All those protons that you theorize are now all located in that center spot. Most of the time, when our alpha particles fire, they hit nothing, which means most of the time I see it detect the back end, right behind the gold foil. But every so freak accident oftentimes, what happens? The alpha particle impacts the nucleus. We're now looking at effectively billiard balls. The alpha particle will then eject backwards, and we will start to see things detect on the back end of the plate. Kind of a neat experiment. Okay? That then gives us the existence of a nucleus. Nucleus, what's our Greek, Latin root for nuke? Are you going to help me out there, Greg? Oh, dang it. Okay. I always refer to the nuke and then just say, oh, it means nucleus. So I can't use the Greek root on there. It's probably center or something along those lines. Okay. So we invented the term nucleus to represent that center portion where all the protons are located. And all the electrons are now a sea around that nucleus. What is it?
Nucleus, little nut.
Little nut.
Nucleus means little nut.
Kernel of a nut.
Okay, kernel, I can accept that. All of our protons are in a tiny little kernel of our atom. Okay?
The analogy that they used in the textbook was great. With,
Superdome?
yeah.
We're going to look at that in the next section. But before we even get to our superdome, what's, actually maybe we can do that. Yep, I can do that. If we look at sizes, we're still looking at things in time insanely small. An atom has a diameter of about 10 to the minus 8 centimeters. The nucleus is 10 to the minus 13. 8 versus 13. I said 4 in the last class. That's 5. So if I was 8 versus 13, that's only a 5-year span. That's not that big of a deal. I mean, some stuff changes then, but not a big deal, right? Okay. Let's actually scale that and get it out of the powers of 10, because the powers of 10 can be oftentimes confusing. Okay? The human brain doesn't deal with big numbers well. If we take an atom and size it of the superdome, the nucleus would be roughly equivalent to a marble inside the superdome. That's a pretty massive difference. So when I'm talking about the size of the atom, which particle am I referring to? The protons or the electrons?
The electrons.
The electrons.
The electrons. The protons are in the marble, the nucleus. The atom itself was the superdome. So when we think about size, we're not talking about mass, we're talking about the volume in which it occupies. That volume is going to be due to our electrons. Okay, so that's a neat example. Okay.
DeGrasse Tyson said there was some general who was trying to walk through a wall because in his mind, like, since the atom was empty space, he thought he could walk.
And there's all sorts of crazy analysis that you can go from this. Rutherford also came out and said that we also have to have a neutral particle in addition to protons. Why? Okay, he didn't have evidence of this. He just said, this is my theory. We have proof that we now have a nucleus, a kernel, and I know I now also have to have a third particle. I can't have just electrons and protons. There's a third thing. Why? What do you got, Ian?
For like both charged things hitting off of the same points.
Getting to the right idea, what happened with our electron as it was floating down towards that negative plate?
It rejected, it pushed
It
away.
repelled. Like charges repel. Opposite charges will attract. If I take all of the protons and I put them in the size of a marble, what am I doing with all that positive charge?
Just like being a centerized.
I'm putting it all right next to each other. What are those positive charges going to do?
Push away.
Repel. Okay? They have to repel. They're similar charges. But if Rutherford's right and we have a nucleus, they can't repel. Why are they not repelling?
Attached to the neutron.
Something is holding them there. We have a glue. That is what Rutherford is predicting. He's saying because we now have this super dense nucleus of positive charge, we also have to have something else that holds them there, that allows them to stick. That is, whoops, not that part. It's supposed to be written in here. That is the existence of our neutron. That wasn't experimentally discovered until James Chadwick, I think 20 years later, came through and actually said, yep, here's a neutron, we have it. Right? So Rutherford's model, while it worked, didn't have evidence for all of the pieces. He just kind of said, here's some stuff. That means these have to be here. I now have a nucleus. That means I also have to have some more stuff, but I don't have evidence of it yet. Okay? In kind of a grand scheme of things, of connections that you will make, I will not reveal that answer. Okay? James Chadwick came back and discovered our neutron. So, 3 subatomic particles. We have an electron, a proton, and a neutron. We look at our table here, big, bold, red. Why big, bold, red? You need to know everything in that table. Okay? So, electron, proton, neutron. Okay? If every time we talked about an electron, a proton, and a neutron, we had to write out electron, proton, E-L-E-C-T-R-O-N, P-R-O-T-O-N, N-E-U-T-R-O-N, probably get a bit irritated, right? Okay. Since no one's agreeing with me, what I'm going to ask you to do, Bart Simpson style, write electron 20 times. Yeah, just the word electron, E-L-E-C-T-R-O-N, 20 times, right now. And I'll time you. Once you've got it finished, hold it up so everybody can see it.
I just press Control V.
No, you got to hand write it. Superdome. It burns? Okay, that's getting somewhere. So is it a bit tedious to write out each of those words?
Yes. Very
Yes. Okay, thank you. Thank you for agreeing with me, finally. Let's not do that again. Okay? So what do we want to do? Like, oh my God, that sucked. Don't make me do it again. Abbreviate. That's where we bring in our symbols. What symbol are we going to choose for electron? E,
First letter of
proton.
the word.
P, neutron. N, why did we not use X, Y, and Z?
Using.
It needs to be really.
First thing that came out was confusing. Why would X, Y, and Z be confusing?
You don't know what that's
Easy myself.
X, Y, and Z are used as our coordinate axes in mathematics, okay, and in physics. We don't want to use symbols that have already been used somewhere else, okay, or we try to avoid it as best as possible.
Use them in the same sentence, like this atoms in this axis.
Yeah,
Like
the
X, Y, and Z is
X
Y, and Z.
electron was moving in the X axis could get confusing, okay. The other confusion part of it is you might have said E because
Starts with the first letter.
electron begins with E, okay? One of those little Sesame Street things. P, proton. So it matches. What other notation have we added to those symbols? If we take a look where do we see that charge? Here it's being said over here. The top right corner, we specify the charge on that particle. So notice if we take a look across, we've got the charge listed out. Okay? Remember, this is the relative charge, not the absolute charge. Okay? We're just trying to add that information into it so that now when I write it out and I say E minus, that's an extra little bit of information that now I go, that's actually an electron because I know electrons are negatively charged. That's not E for elephant because elephant begins with E. Kind of make sense?
When you say it's a relative charge, what's it relative to? Whatever it's in?
Each other.
So
Right?
there's no base.
So it could be like I'm tall and you're short.
0 is just
We don't-
relative. It's 0 is relative to
0 mean it doesn't have a charge.
Okay, so that's
That
relative.
could be kind of your relative position there. There is something negative from the 0. Yeah. Okay, and then the neutron doesn't have any charge associated with it. Okay. Mass. Mass is not actually listed in this, okay, as part of our symbol. Okay, and that's largely because the mass is simple enough that we just kind of assume it. If we move to our mass column, we have 3 mass values that we would have to memorize. Neutron, relative mass again is 1. Okay? So we aren't saying exactly what it is. We're just saying compared to the other subatomic particles, I'm going to define the neutron as 1. Well, when I look at the proton, guess what the proton weighs?
1.
The same thing as the neutron. So when I'm comparing my particles, I can say 1 now is kind of an arbitrary unit. We could do the same thing with weight. We went through and said, I am by definition 1. Y'all are probably less than 1. Right? Because I'm heavier than you. Right? That's what we've done here. Why did we use those relative charges or relative masses and not actual masses?
Because if you would have compared it to like by weight, it would have been negative.
If we use an actual mass measurement or a mass unit that we're used to seeing, the number gets mind-bogglingly tiny and becomes confusing to work with. So we pick a relative value. That simplifies our interpretations. Make sense? Okay, so that explains proton and neutron being nice. What about the electron? What the hell? So we said we picked this arbitrary unit to simplify our numbers for protons and neutrons, and yet we move to the electron and we get 1 over 1,836 mass units. That's not an easy number. But as Ian was starting to suggest here, what is that unit or that measurement actually approximating? Zero. If I rip a piece of hair off my head, does that piece of hair have mass?
Yes.
Yes. If I now stand on a scale, okay, and I weigh myself, holding on to that piece of hair, okay, I've got to weight. I now let go of that piece of hair. I have technically lost mass, right? Am I now excited because I'm now losing weight? No, why not? The amount of mass contribution from my hair is negligible in comparison to my total weight.
It'd be like trying to weigh the moisture coming out of your mouth as you exhale.
Exactly right. Same thing is happening with our electrons. The electron mass is so tiny that we can ignore it. It does not contribute mass to our atoms. All right? For pace on this, are we going too fast or too slow? Up for fast, down for slow. Okay, well, actually not too bad. Okay, we'll pick it up a little bit. Atomic notation. Okay, the textbook labels atomic notation horribly. It's not atomic notation. Okay, what it is actually is nuclear notation. Okay? What we are labeling with what they're calling atomic notation has everything to do with only one part of the atom. What part of the atom? The nucleus. Hence, it's better called the nuclear notation. Who might want to use nuclear notation? Nuclear physicists. Okay. How many of you plan to be a nuclear physicist? Ooh, interesting. So this notation has some questionable validity for our everyday use. Okay? Because it's applying primarily to the nucleus. Okay? Unfortunately, that doesn't mean you aren't responsible for it. You are still responsible for it. So we want to go through and label the different aspects. We have the atomic number. Okay? That is the characteristic that defines the element. Okay? What of our three particles defines the element? For those of you that said we were going slow, should maybe jump out with some answers. What defines the element? Only the protons. The neutrons do not define the element. The electrons do not define the element. Protons define the element. So when we're looking at our atomic number, that's really just a fancy way of saying the number of protons in our sample or in our element. Okay? The mass number. Well, as that starts to suggest, what is mass? Well, it's going to be the things that have weight. That's going to be the sum of our protons and neutrons. Make sense? What is the SY? That's the symbol for our element. No one may say it, but you can still jump in. Okay, so we could pull elements off our periodic table. We could pick indium, and we could then try and find the relative or the appropriate notation associated with this. You are responsible for knowing the mass number is located in the upper left-hand corner and the atomic number is located in the lower left-hand corner. Okay? For your view, that would be left and left. Right? Does that make sense? Okay? Please find the atomic number then for boron. Let's switch it to carbon.
6.
Okay? I've heard 6. Where's the atomic number according to our notation?
Should be on the top.
Atomic number according to our notation. Where is it found? The atomic number is found in the bottom left corner. What is the number on our periodic table for carbon found in the lower left-hand corner? 12.01. Is that the atomic number for carbon? No. How would you know that's not the atomic number? 2 valid answers coming out of this. One of them is you used the key, and when you look at the key right in the middle with that bromine, where does it say the atomic number is located? In the top right-hand corner. Okay. The other answer is that you happen to know what the atomic number was out of the gate. Okay. Why the sudden change from our nuclear notation to the periodic table?
This is for like when you're doing things like reactions and stuff, and this is for just labeling.
It really doesn't have much to do with reactions because you will probably never use this notation outside of just labeling it.
Is it because the numbers are set like right next to each other that if you were to go look it up, you could mistake the numbers for the other one?
It's not a bad idea. For clarity, we're trying to separate those numbers. Okay? So there's kind of an organization, an aesthetic, if you will, of our periodic table to separate those numbers. What are you talking about? Remember, when we're looking at nuclear notation, we're concerned about radiation. Well, radiation is looking at the nucleus and its structure. Well, the nucleus has different numbers of protons and neutrons. The larger we get, the more neutrons we have to add in. And what eventually happens to elements, say, like uranium? They have nuclear radiation. What is happening in that nuclear radiation? The nucleus is falling apart.
Let's say, isn't it degrading?
It is changing its mass. So a nuclear scientist is going to want to highlight what? The mass of the species they're looking at. So they'll put the mass in the upper left-hand corner because we, as most English writers, read from left to right and from top to bottom, which would suggest our nuclear scientists, the first thing they're going to see is the mass number and be like, oh, that's the mass number associated with this symbol. I now have a concept about what that thing can now do. Why do we not do that on the periodic table? How is the periodic table organized?
How about metals, metalloids, and gas?
So we had a metal, metalloids, and nonmetals organization to it, yes? What else? After hydrogen, we get helium. After helium, we get lithium. After lithium, we get beryllium. We're reading it left to right, top to bottom. Hydrogen. What numbers are associated with hydrogen? 1 and 1. Helium. 2 and 4. Lithium. 3 and 7. Okay. Beryllium. 4 and 9. Anybody notice any patterns here? So we could look at the atomic weight and start to compare that back to the atomic number, but that's not comparing the different elements. I compare hydrogen to helium. I don't care about the atomic weight relationship.
It's protons and neutrons.
The atomic number. Hydrogen is first, followed by helium as second. What number do we use for second? 2. What was third? Lithium with 3 as its atomic number. Beryllium with 4. Our periodic table is organized according to the protons, the atomic number only. Right? So why is our periodic table changing the organization now? Because the periodic table is trying to call attention to the number of protons for each of those elements. Because the protons defined what? The element we're looking at. Right? Nuclear scientists care about the mass because they can then start to predict something about that element decomposing. So they use a different notation.
Is protons also what like determines whether which elements can bond?
We'll look at bonding, and I would completely disagree with probably any way you were taught how to do bonding.
Okay.
Just so you know.
I thought it was like we're trying to have
We'll
a certain amount of
later. Atomic notation. Mass numbers, protons and neutrons. Atomic numbers, protons. So if we start with the example, which conveniently Word decided to mess with, or PowerPoint decided to mess with my location of letters. What element is it? Silicon. How do you know? It says Si. So we could do it based off of the symbol itself. Okay? The atomic number. Oh, wow. Yeah, it really messed up a lot of stuff. So if you look really, really carefully, what you will notice is there are these little tiny white boxes that were supposed to be hiding a lot of things.
Oh, so you were going to ask us, and we're going to let you.
Yeah, I was going to ask you, and you weren't supposed to see those. Right? So the element with a symbol of Si is silicon. The atomic number is 14. Okay? The atomic number, interestingly enough, in our nuclear notation is the lower left-hand corner, not on top. It's the opposite, remember? Different genre of what we're looking for. A mass number of 29 means what? It's the number of protons and neutrons. So how do I figure out the number of neutrons? You know the number of protons because that's the atomic number. So we can take 29 minus 14, and we'd end up with 15 neutrons. So we attack that.
Something else that's kind of set, like, is it always going to be where there's one more neutron?
Nope.
It's going to change?
Nope. Your parallels, so a question here was, are we going to have always one more neutron than we have protons? Okay. Hydrogen. How many neutrons does hydrogen have? 0. Its mass number is 1. If it has a proton, there's the mass of 1. If we added a neutron, what would hydrogen's mass number be? 2. What happens when we move to helium?
So you added a neutron and it became helium? Or you added
So what happens, so that's a good question. What happens when we move all the way up to helium? From hydrogen to helium, what changed?
You get a proton and 2 neutrons.
We added an extra proton because what happened to the atomic number? It went up by 1. Right? What happened to the mass number? Went up by 3. Well, one of those we can explain by an extra proton. What about the other 2? Those are neutrons.
The electrons are negative.
And then electrons have a 0 mass, so we don't have to worry about the electrons at all. Okay? So if we look at your initial trend, you always have one more. Helium's already an exception. What you will find is if you go through and calculate it for every single one, in general, for every proton, there's a neutron. All the way up. As you get heavier and heavier, you end up having to add more and more neutrons. Okay? If I wanted to glue marbles to each other, okay, I could use a little bit of glue to glue 2 marbles. If I want to glue 3 marbles together, what has to happen? I add even more glue. 4 marbles, more glue. 5, 6, 7, 108. There's now so much glue that in the process of putting that together, the inside probably did not dry before I added the rest of them on there. Which then means what happens?
Unstable?
It's unstable, it falls apart. When it falls apart, it's going to release individual pieces. Those pieces were our nuclear radiation.
So some of these have like the atomic weight in parentheses. Is it just theorize that?
Which ones have the atomic weight in parentheses?
Synthetically,
The man.
All the synthetically man-made ones.
So why
That's
does
because
the-
we've only found 1 atom or 2 atoms of it. The only ones that have formed that are stable enough have exactly that number of protons and neutrons.
What about the one that has no atomic weight? They just have no idea. They're just like actually fast.
Did they make it?
Or is it just theory?
They weren't able to observe the actual existence of its mass, so they can't officially report it when the table was made.
Have they figured it out yet?
I think so. So, atomic structure in the periodic table. Okay. What you guys should be able to go through and do, and I'll give you 30 seconds, is fill this in as best you can. Okay. Get all that information in there. Feel free to talk to the people around you, see what you can come up with. What we're going to leave it on is those meanings. Okay. I want to know what electrons mean, what protons mean, what neutrons mean. Those would be like, well, that's like asking me what a soda means. Yes, it is. Right? It is a difficult question to answer. We will pick up with that, or at least my explanation of the meaning, on Thursday. Let's see if you guys can get most of that filled in. Because we only have 30 seconds, let's go ahead and start. Electrons, located where? Outside. Protons. Yes, we could say inside, but let's say nucleus. Be a little bit more specific in that. The mass of an electron. We could do negligible, but remember you have an instructor that can't spell that word, so that doesn't work.
1/800, 1/18.
0. 0. We don't memorize a bunch of useless numbers. Okay, protons. 1. Neutrons. Charge of an electron. Charge of a proton. Neutron. Okay. The symbol for a neutron.
Oh, N.
That was me being a jerk. I said for a neutron, it's N. Protons.
P.
Electrons. E. Can we add more information to make sure those are clear?
Yeah, but a negative sign, a positive sign.
Negative sign in the upper right-hand corner, positive sign in the upper right-hand corner, and a 0 in the upper right-hand corner. Interesting thought coming back to the meaning. We've not talked about what we're specifying in the upper right-hand corner exactly. Okay? That can help us contribute what we're talking about when we look at the meaning. Okay? Arguably, we did talk about one. What does it mean if I have 12 protons?
Well, these protons, then it's fire.
Okay, so some people have picked it up. Okay? And as far as I can tell, only one person actually said the answer. Okay? Several wrong answers were also said. Okay? Think about the meaning for your electrons, your protons, and your neutrons. We'll pick up there. It's an important concept to kind of get across that can help simplify what we're looking at.